We're going to take a look at the process for graphing an absolute value function. In this section, everything we look at will be an absolute value of a linear expression, but the idea that we establish here for graphing it would still apply to absolute values of other expressions as well. What we're going to do is start by just removing the absolute value temporarily. So we can see that what we started with was f of x equals the absolute value of negative 3x plus 1. We're going to lightly graph the line that we get when we remove the absolute value. And this isn't going to be our final graph, but it will help us get to the final graph. So in this case, we can see that we have a slope of negative 3. So I would think of that as negative 3 over 1. And I have a y-intercept of 1, so that graph is going to pass through the point 0, 1. Looking at this graph, which is already drawn for us in this case, here's our y-intercept of 0, 1, and here's our slope of negative 3. As we go right 1, we also go down 3. So that's how we would get that line to start with. Now, if we look at the graph we have and we think about what the absolute value does, for example, this point here is 1, negative 2. So that is saying that y is equal to negative 2. Well, f of x is the absolute value of y, and therefore f of x is the absolute value of negative 2, which is positive 2. So the way we get from this point to a graph that's on the actual, to a point that's on the actual graph of the function f of x is we replace this negative y value with a positive y value, which is the same thing as reflecting this point up about the x-axis. So instead of a point at 1, negative 2, I want this point to be at 1, positive 2. And then I can do that with all of the points that fall below the x-axis. This is at 2, negative 5. I'm going to bring it up to 2, positive 5. But I need to make sure that the point where I turn this around is where it touches the x-axis. So I turn it around at the x-intercept, and I go ahead and connect the remaining points with a line. This turns the graph into a V shape. Then I can come through with an eraser and try to remove the part of it. This is why I graphed it lightly in the first place. I'm going to try and remove the part of it that was below the x-axis in the first place, so that my final graph is a V. We'll make it a little bit more bold now so that it stands out. My final graph is a V that touches the x-axis and then turns back around. This does keep going, so we can put arrows on the end of the V, but it never drops below the x-axis. A very common application of absolute value is distance, since we don't tend to describe ourselves as being a negative distance from something. In this example, we have an airplane flying directly from California to North Carolina, and it's going to fly directly over this Oklahoma City airport. The speed is 600 miles per hour, and we can see that reflected in the slope of the positive slope side of this V graph. We can see that this would be a run of 1 and a rise of 600. So where we have a positive slope in our absolute value graph, that corresponds to a speed of 600 miles per hour. And if we look at the negative part, this looks like a slope of negative 600. That just means the rate of change of the distance from Oklahoma is decreasing as we're getting closer to Oklahoma City, and then it is increasing as we're going away from Oklahoma City. But in both cases, the speed we would refer to using a positive value. We're going to use this graph to answer a couple of questions. At what time is the airplane 600 miles from Oklahoma? So we can identify 600 miles here on the y-axis, and then draw a line corresponding to that 600 mile mark. And this is going to be 600 miles at two different points. Indicate them here and go ahead and identify the times. It looks like at 2 hours and also at 4 hours. So after 2 hours and 4 hours will be exactly 600 miles from Oklahoma. One on the approach and one as we're getting farther away. We can also look at this question, at what times during the flight is the airplane more than 600 miles from Oklahoma? For that, we're going to want to think about this in terms of inequalities. This part of the graph and this part of the graph both correspond to distances of more than 600 miles. So we have two intervals here for our answer. We'll say, looks like between 0 and 2 hours. And also between 4 and 5 hours. The way that we just answered these questions from looking at a graph is very similar to how we solve absolute value inequalities by looking at a graph. But once the context is more abstract, it's not as obvious how to find those answers. So we're going to replicate this process now with an abstract example. We will start by just graphing y equals y equals the absolute value of 1/2 x minus 3. And remember that the way we graph absolute value functions is we first graph y equals 1/2 x minus 3, which we know how to graph because this is a straight line. This has slope positive 1/2. It also has a y-intercept of negative 3. So I'm going to start by just graphing this line. I'm going to do it fairly lightly, so I'll start with a light color and a thin line. I have a y-intercept of negative 3, and my slope of positive 1/2 means every time I go right 2, I'll go up 1. So this gets me several points on the line, and I'll go ahead now and connect those points, and a little bit in this other direction as well. The next thing I do is I find the x-intercept and lock it down. The x-intercept is always where the line turns into a v. Even if the x-intercept doesn't happen at an integer value, even if it crosses at a fraction, that's always where we lock it down. We never turn it around at a different point. So I'm going to lock it down at the x-axis, and each of these points I will reflect up to be above the x-axis. The ones that were already above can stay where they are, but the ones that were below are going to be reflected the same distance from the x-axis, but going up instead of down. And now I will create a V. Like this. This does have arrows on the ends. I'll draw those just so that I don't forget. The graph doesn't end as soon as it gets to the edge of my grid. And it's helpful to come back and erase the part that we drew that's not really part of our graph. But since we drew it in so much lighter a color, it would be okay to leave it, as long as it's really clear what part of the final answer is really in your graph. Okay, so this is y equals the absolute value of 1/2 x minus 3. We're going to use this graph to solve 3 different equations. For the first equation, I want to look at intersections with the line y equals 2. This is a horizontal line, so I'll go ahead and draw that in right there at a y value of 2. And look for the intersection points. We have one here, we have one here, and because this equation is only an x, I am only interested in the x coordinates of these intersection points. I do not want to enter the whole ordered pair as my solution. It looks like these intersect at 2 and at 10, so my solution set consists of just the two values 2 and 10. I could write this as x equals 2, comma, x equals 10. That would be fine. I do not want to write it as an ordered pair, right? This 2 comma 10 in parentheses could either mean an ordered pair or it could mean the whole interval from 2 to 10. In both cases, it's wrong. So what kind of brackets or parentheses we use really does matter. It has a completely different meaning if we use a different bracket style. These curly set braces here really mean just a list of numbers. The only numbers in the list are 2 and 10. Let's also consider y equals 0 for this next one. Y equals 0 is the same as the x-axis. So when I draw it, it's a little bit hard to see. I'll label it on this side just because it's a little bit, I have a little more room over here. And in this case, it looks like we get only one intersection. So our only solution is the number 6. Again, I could just say x equals 6. That would be an acceptable way to answer this. But our solution set consists of only the number 6. And finally, we have -2. So if I graph y equals -2, that is another horizontal line down here below the x-axis. And I can see they don't intersect at all, and no intersection points means no solution. So from this, I can see that there are 3 possibilities. I might have 2 solutions. I might have 1 solution, and I might have no solution, depending on whether the number on the other side of the equation was positive, 0, or negative. This is what we use to set up our process for solving these symbolically.